January 2016 M2 paper. This is the first part. We'll do the first 4 questions. First question is a power question, or work energy and power question, fairly standard situation. We've got a weight of 900 G and it's been pulled up by some driving force. By a certain distance. Now we're told it's gone for 10 seconds at a speed of 14 meters per second, so that's not difficult to work out. That the distance it's moved up is 140. We're certainly going to need that. We've got resistive force as well of 800 newtons. Now there's a couple of ways of approaching this problem. I'm going to use energy because because it's necessarily the best way of doing this question. I don't think it matters too much. Most students, I think, would resolve and work out what F is here, which wouldn't be too difficult to do, and then times the answer by 140 to get the work done. So it's not a problem doing it that way. I'm going to be slightly different, partly because sometimes in the exam they say using energy or use the work energy principle. So I'm going to use the work energy principle just in case a question in future says using energy, which they can do. So use work energy principle. Let's write that further down because I'm going to need that diagram bit there in a moment. Work energy principle. I like to summarize it in this one formula, and we can adapt this formula to basically any situation. That formula basically summarizes the work energy principle. Obviously, this speaks for itself. Delta KE, that's any change in kinetic energy. This is any change in potential energy. These two together are sometimes called mechanical energy. Any change will be equal to work done by any external forces. Now, often there's only one, sometimes there's two. There's two in this case. External forces are basically forces other than gravity. Okay, so because they're going to add or take away mechanical energy from the system. So we can, just as I said, we can adapt this formula. I would, first of all, this bit obviously is not relevant here because it's continuing, although it has kinetic energy, it doesn't change. So it's the change in potential energy here. We've got two forces. That's the frictional force, the driving force, sorry, and we've got the resistive forces. So let's just summarize this then let's just write this up. To change in potential energy, let's go back to red again. We're going to need the distance here. Well, we know the angle here, theta, we know that, and we know, so this is 140 sine theta, but we know sine theta is given as 1 over 25, so that's 140 over 25. Okay, so that's the horizontal, the vertical distance moved. So that's our change in potential energy. mgh is potential energy. The mass is 900 kilograms. So it's 900 times by 9.8, which is g, times by the vertical distance, which is 140 over 25, is the change in potential energy. Now that's going to be, we want the work done by driving force. But there is another force in play here, and that's going to be taking energy away from, that's going to be losing mechanical energy from the system. And that'll be 800 times 140. So that means the work done, because F times D, just in case F times D is the work done. So the work done by a driving force, take away the work done by the resistive force, is equal to the change in potential energy. So that gives us, if we work that out, work done by driving force, we can rearrange that nice and easily. That's going to be equal to when you work it out, 161,392 watts. But we really want to be giving that to two significant figures or three significant figures. So 160 kilowatts is our answer. I'm given two because we're using G in our answer, but 3 is fine as well. Okay, so 160 kilowatts is our answer. Notice I didn't have to work out the driving force here. If it had done, I could just divide by 140 to work out the force, because that amount there is FD, but it doesn't ask for that, so I haven't used it. Okay, I thought that was quite a nice way of doing it, using work energy principle, although obviously it's no more or less efficient than resolving and working out F and then times it by 140. Okay, part B now says that if we look at part B, it says when the car is at B, that's travelling at 14 meters per second, the engine suddenly increases to P kilowatts. So let's call, obviously the driving force now will be different to the one before, but I haven't really dealt with it before, so there's no confusion. So that's F. $800 is the same. Obviously we've got we've got gravitation, and now it's accelerating at a rate of 0.7 meters per second squared. Okay, now we've got the weight acting down, obviously, that's 900 G, and we've got the angle here, theta, which we know is arc sine 1/25. So if we apply F equals ma, we have force, take away the driving force, take away 900, the component of the weight, which is 900 G sine theta, take away 800 is equal to mass, which is 900 times by 0.7. So that gives us the force is 900 times 0.7, which is 630, plus 800, plus 900 times 9.8 times 1/25. Okay, so that, if we work all that out, it comes to 1782.8 newtons. So now we're just left to work out the power. Well, we know that power is force times velocity, and it is just at that instant at the beginning where it's got the same speed. So we've got P is equal to 1782.8 times by 14, and that comes to 24959.2. But remember, it has asked for, well, it has asked for a value of P, which is in kilowatts. So that's P is equal, so let's make sure we leave watts there. P is equal to 25 kilowatts to two significant figures. It's also okay to write 25.0 kilowatts, three significant figures, but 2 is fine here because of the use or implication of G in the answer. So, okay, that's question 1 done. Let's have a look at question 2. So we've got a collisions question. We've got a particle P of 0.7 and a particle Q of 1.2. So it's 0.7 kilograms and 1.2 kilograms. It's P and Q. They collide. Q is at rest, so that's got no velocity. And P is moving with velocity 6 meters per second. So that's our before situation. Afterwards, it does tell us they move in the same direction. That's going to help us get our inequality. Call them V1 and V2. So let's just apply momentum, conservation of linear momentum. We have 6 times 0.7 plus the velocity of the momentum of that, which is 0. Okay, plus the is equal to 0.7 V1, because that's P, and this is Q, plus 1.2 V2. So that gives us 4.2 is equal to 0.7 V1 plus 1.2 V2. Okay, might as well multiply it out by 10, so to 7 V1 plus 12 V2. Okay, now let's also, as is normally the case, we set up 2 equations, one being Newton's law of restitution, which basically says E is equal to speed of separation over speed of approach. Well, V2 is clearly more than V1 here because it's moving away. So the speed of separation is V2 minus V1. And it's going towards it at speed 6. So we have V2 minus V1 is equal to 6E. Now, if I can get an expression for V1, then I can then use the fact that it's going to be positive to get my answer. So let's just substitute for V2. Okay. So V2 is equal to 6E plus V1. So substitute for V2. So I'm substituting my V2 into there. I get 42 is equal to 7 V1 plus 12 times 6E plus V1. Okay, so that gets me 42 is equal to 7 V1 plus 12 times 6, which is 72E, minus plus 12 V1. So I have 19 V1 is equal to 42 minus 72E. Now, because there's no change of direction, so V1 must be greater than 0. So that gives me 42 minus 72E is greater than 0, which gives me 72E is less than 42. So that gives me E is less than 42 out of 42 out of 72. and that simplifies down to the required result. So E is less than 7/12 as required. Okay, so now it says given that E equals to 1/4, find the magnitude of the impulse. So we can put in 1/4 into these expressions and just work out what V2 and V1 are. So we've already got this 19 V1 is equal to, so if E is 1/4, let's just sub 1/4 into there, is equal to 42 minus 72 times 1/4, which is V1 is therefore equal to this 42 take away 18, 24/19. We can put that back into here as well. We can work out V2. So V2 is equal to 6 times by 1/4 plus 24/19. So that comes to 105/38. Exactly. So it says find the magnitude of the impulse exerted on Q in the collision. Now, the impulse on Q is actually just going to be, it's gone from 0 to moving off with velocity 105/38, and the mass is 1.2. So impulse is equal to change in momentum so that's equal to just the momentum afterwards, which is 1.2 times 105/38. (63/19). We might be so 63/19 or 3.32 Newton seconds. That's that question now done. Before I move on though, just to make it clear, the mark scheme does say explicitly they want a positive value because it's talked about the magnitude of the impulse. That basically means we're not concerned about whether the impulse is in which particular direction it is. It actually is positive anyway, depending on which way you took positive. That's not the point. It is that we need a positive answer there, which is why I haven't bothered with putting into just MV minus MU or whatever. I just looked at the thing and looked at change of momentum, ensuring that the answer was positive. Okay, let's move on to question 3. Okay, so it's a variable acceleration motion in 2D, vectors question. Right, okay, so we've told that it at some point A at time t, it's got travelling with that velocity. The key thing here is that the I and j are the same. So all we're doing, we're not needing to differentiate or anything like that at this stage. All we're doing is equating for the particular value of t, which is big T, the two expressions. Okay, so that gives us 3t squared plus 6t minus 24 equals 0. So just divide that by 3. we have t squared plus 2t minus 8 equals 0. So we get t plus 4, t minus 2 equals 0. Clearly the negative one's not appropriate, so we've got t equals to 2 seconds. Okay. Now the acceleration, we just differentiate our expression from above there to find acceleration. So we've got acceleration is equal to 12ti. Oh, let's put the I outside. 12t plus 6i plus, and this, the 24 goes, that's just 6tj. Okay, nice, quick and easy 3 marks for part B, not much to do really. And then part C, now it starts talking about the distance OA. Now remember, we've already worked out the time it takes to get to OA. So we're told at time t it's at the origin, so that's going to give us c is equal to 0 when we integrate. But let's just work this out. S is equal to the integral of v dt, or let's call it r because we're in 2 dimensions here. So that's the integral of v dt. So that's equal to this integrated. So that's 6t squared integrated is equal to 2t cubed plus 6t, which integrated, which is equal to 3t squared. That's I, plus, for the j bit, t cubed plus 24tj. And now, of course, normally we're going to have c1 and c2 some constant because it's going to start at some point. But it does say, I'll write it here, but you probably get away with that. We probably don't really need to write it for the exam purposes, but it might be in another question, so we've got to be careful with these things. So when t equals 0, r equals 0, so that means that c1 and c2 are also equal to 0. So we have r equals 2t cubed plus 3t squared I plus t cubed plus 24tj. Okay, so let's put in the value of t that we know. So when t equals 2, we have r equals 2 times 2 cubed plus 3 times 2 squared I plus 2 cubed plus 24 times 2j. So working that out, that's 16 plus 12, so that's 28. 28, oh no, that's 28i plus, and that's 8 plus 48, so that's equal to 56j. But we want the distance, which is the magnitude of r at this point. And t equals to 2, or RA we could call it, just to, and that's equal to 28 squared plus 56 squared square rooted, which is equal to 28 the square root of 5, which was accepted. A third is fine. Or we want to give 3 significant figures here. It has to be 3 because there's no g. 3 significant figures. Okay, that's it. Just looking through the mark scheme, just realised that there were 3 quick marks for that. Of course, we've got to, it wants the acceleration when t equals to 2 for that, because it wanted it at the point A. So it's a good lesson for us all there. That will give us 30i plus 12j. Read the question, make sure you've answered it. Okay. Right, so that's question 3 done. Let's have a look for question 4. Oh, it's interesting. It's work energy again. Now we know on question 1 why they didn't insist on work energy, because they knew they were going to test it later. Okay, well, first we've got a pulley situation here. We know the angles given. We know masses. And I suspect there's going to be friction. Yeah, because we talk about the coefficient of friction. And the system's released from rest. Find the work done by friction as P moves from A to B, so the friction must be limiting because it's moving in that direction. Okay, I think we're going to need to work out that friction just times by 2.5 to work out the work done by friction. We've got tension here. So let's work out the frictional force first. We're going to need to resolve perpendicular to the slope to work out R, therefore work out F. Okay, let's make a bit more in there. Okay, so we've got F equals, oh no, not F. Let's resolve perpendicular to the slope. And that's going to get us R. We have R is equal to mg, so that's 2g cos alpha. So R equals 2g times by cos alpha. Now cos alpha is going to be 4 over 5. We should hopefully be used to this kind of transferring between angles here. So that's 8g over 5. So we have F equals mu R because it's in limiting equilibrium. So we have F is equal to a quarter times 8g over 5. So that's 2g over 5. So the work done by friction or against friction, same thing really, work done against friction. That's basically what that means is what part of the tension is going to counteract the frictional force. So it's going to be that times 2.5. So it's 2 over 5g times 2.5, which is 5 over 2. So it's equal to g, or 9.8. Put the units in for good measure. Jules, find the total potential energy lost by the system as P moves from A to B. Right, now we've got the system, the whole system means both of these particles here. So we need to look at because this one will have gained in potential energy and this one will have lost potential energy. Okay, so potential energy lost will be equal to the loss of this potential energy, which is going to be equal to 4 mgh, 4 times g times 2.5. Take away, because this energy is going to be gained, if you like, double negative. Now remember, this is, you've got to make sure you apply the trig here, because the vertical distance is moved, is 2.5 sine 2.5 sine theta. So it's going to be equal to 1.5. In fact, the vertical distance that's moved. So that will be equal to 2g times by 1.5. So this energy has gained it, this energy's lost it, but if we work those two out together, that will give us the answer 7g, or 68.6. Again, let's put the 68.6, let's put the units in again. Okay, so that's part B. Right, it is definitely lost though, so they would have accepted a negative answer, so I'll put that in brackets here. Lost. So change in, so delta PE is equal to minus 68.6. Okay. Right, now work energy principle. And now they've told us to use a work energy principle, so we really shouldn't use any other means. What we can do is say delta Ke, that's the increase in potential energy, take away the add the change in potential energy, which happens to be negative here, equals to work done by friction in this case. Because there's there is tension. You might think that counts, but the tension force is not going to change it, because it's going to increase one and decrease the other, so that doesn't count in our calculation. So it's work done by friction or work done against friction. Work's done against friction or work done by friction, and we've worked that out already. That's this number here. So we have delta Ke. So the delta Ke is equal to, now both of the particles are going to have acquired potential energy. So that's half times by 4 times v squared, plus a half times 2 times v squared. Take away 68.6, because it's lost potential energy, is equal to the loss, because the friction is only going to take away mechanical potential energy, so that equals to minus 9.8. Right, so working that out, that gives us 3v squared is equal to 9.8 plus 68.6. No, 9.8. 68.6 minus 9.8, should I say. So that's 58.8. So v squared is that divided by 3, which is 19.6. So v is the square root of 2g, or square root of 2g, which is equal to 4.43 meters per second. And that's question 4 done. So we'll do the other 3 questions in part 2 of this video. Okay.